Good morning, everyone. Thanks for joining us today. We're going to talk in this session about fine-grained and centralized authorization. For OpenStack, we're going to do that with OpenPolicy agent. So we'll talk about what OpenPolicy agent is and how we integrate it together with OpenStack. So, Artem, maybe you want to introduce yourself?
Yeah, okay. My name is Artem. I'm working at CNCF. I'm working as an identity access management architect there. I'm also PTL for Keystone, but that's not the point. Yeah, please, Adrien.
And my name is Adrien. I'm a French guy also working for CNCF, which is a German company. So we are colleagues with Artem. I've been involved in OpenStack in different ways, mainly as an operator for different companies for more than the last decade or so. And just a word on CNCF, where we are working. It's a company headquartered in Berlin, and mainly we are a public cloud provider. So of course using OpenStack, and we have some additional services with, of course, like managed Kubernetes on top of it and other things. So what we are going to talk about here, it's coming from some needs of our customers for our public cloud, and we'll talk about how we actually use the solution, and we do use it for our production public cloud. So the agenda today will start with giving some context about, I think maybe you know already if you operate a cloud, but we go quickly through that about how authorization works in OpenStack. And what we are trying to solve, how we ended up with this OPA thing for OpenStack. Then we'll go a bit deeper into OpenPolicy agent itself and how we integrated with OpenStack, what were the challenges here, what solutions we came up with. We'll cover, there are a number of architecture questions running OPA alongside OpenStack. And we'll have a special highlight on Neutron for reasons that you will understand. It's not so easy for Neutron. Artem will tell you more when we get there. And we'll finish, the last part will be more about our production experience. So how we approach the rollout of this OPA solution in our production cloud. Obviously trying not to impact our users on causing any downtimes. Talk a bit about how we are monitoring the system and what we learn from that, especially in terms of performance impact. And we'll tell you a little story about this timeout issue we had and that we kind of not completely fixed yet. We walked around for now, but eventually we will find a real fix. So authorization in OpenStack. You probably know this Oslo thing, which is like the set of common libraries that are for all the functionalities that all OpenStack services or many OpenStack services need, and one of them is oslo.policy that is used by, as far as I know, like all the OpenStack services on the API level to deal with the authorization and applying policies. So basically, to know if a user is allowed to do what he is asking. The way it's working in OpenStack is a mix of airbag and ABAC, so role-based access control and attribute-based access control. I think the role-based access control part is the easiest to understand. Also, if you're assuming you're familiar here with OpenStack, you know that there is this concept of users and projects.
And you think that this is RBAC, that OpenStack is based on RBAC, but it's not really.
At least your users usually have some roles on projects, so you see the role-based access control. But it's not only it. There is some attribute-based access control. I think one example that we can give here maybe makes sense is if as a user you're trying to list or get some detail about an image in glance. If this image is public, then it impacts whether you can see it, whatever the role you have. So like an image being public is an attribute of the image, like the visibility, is it public or not? And so this kind of things is also taken into account. So each policy, what we'll call a policy in OpenStack, basically will, so for example, get image. This will describe the cases where the user is allowed to perform this operation. by default, there is these roles which exist. It's not even correct nowadays because there are a couple of additional roles in the more recent releases of OpenStack, but this one you're probably familiar with, at least the default member role, the read-only role, and the admin role, which is like the one that has superpower or across all projects. And one important thing I want to mention is it's going to be important for what we are going to do next is that policies are evaluated for each API request. So if we change the way the policies are evaluated, it can quickly have a big impact, both on breaking everything or on the performance side, because there can be a lot of evaluations needed as soon as you have a lot of API requests. So if you want to customize authorization in OpenStack right now, like with the default upstream code of OpenStack. So first, of course, you can manage your own roles, right? So that's easy. In Keystone, you have API to create additional roles and so on, and assign the roles to users and projects. But if you create a new role by default, it doesn't mean anything, right? You can create a role, call whatever you want. It means nothing until you actually start to use them in the policies. And the policies, they are defined in the source code of the project. So the source code of Nova, Cinder, and so on, the policies are defined in code, and you are able to override them using this famous configuration file, policy YAML. Used to be JSON in the past. Maybe you remember that if you were there already. Now policy YAML, and in here you can override. You don't have to write everything, just what you need to override. And for each line, you have this is the policy, like get image for claims, and then you have one kind of string, which is like kind of Boolean thing that says, if role is this, or if the visibility of the image is public, etc., etc. And you can customize that. The thing is, if you start to trying to do some more complex things, then the complexity you have to embed it in this Boolean thing on one line. In this file. So
some of the Keystone policies are basically 3 lines long, and this is a Boolean expression 3 lines long. It's impossible to actually understand it in the head to build up.
Technically, you can do a lot of things, but then the question of how easy it is to maintain and read, and questions like how easy it is to test, and so on. So you will see that with our approach, we are trying to solve a bit of these shortcomings. One also is whenever you change this policy file, you need to make sure it's redeployed like everywhere. So if you have the Nova API deployed across many nodes, then you need to redeploy it everywhere. And if you are using some older versions of OpenStack and of oslo.policy specifically, you even need to restart the service. In the more recent versions, that's no longer the case. The service will dynamically read again the file. So what we're trying to solve. Quickly, the need from some of our customers was, we want fine-grained access control. What does fine-grained mean? It can mean a lot of things, and the customer itself, the customers, they didn't really know exactly what they meant, but there was a starting point. The starting point was we wanted to provide some service member roles. What I call service member roles is like having a role that only allows compute operation, a role that only allows block storage operation, so like a per service. So nothing so complex, but that was like our first goal, and we said, in order to be able to provide fine-grained, even more complex fine granularity in the future, we want to have framework to do that more easily. So to have more flexibility in managing the policies. We would like to have a central location to store and manage all the policies. We would like to be able to test the policies before we give them out to OpenStack and we test them inside OpenStack. We'd like to make it easier on the deployment side and not having to redeploy manually or as a configuration file to all the nodes, the policy YAML files. And so you already see that OPA would be one answer, and the good benefit also is that, as I said at the beginning, we have OpenStack, but also some other services, and OPA can work with other services, like think about Ceph or maybe Kubernetes, and one idea for the future is that, if we set up some OPA thing, it can be used also for the services in the future. CNCF is is a CNCF project, so that graduated already a few years ago, so it's kind of a mature project. They define themselves as a policy engine, so the work of OPA is to evaluate policies and say to the application, this is allowed or this is not allowed. There are many ways to integrate OPA with your application. It's written in Go, so you can embed it in your Go application directly. You can go do that through WebAssembly, and there is a REST API. And you already see that for integrating with OpenStack, which solution we are going to pick here. It has a specific language called Rego, which is a language that we use to define the policies. So instead of this long Boolean line that you have in your policy YAML, now we will use a different language. Artem will show you in a bit. And there are some interesting features that we will make use of. The policies can be fetched remotely. So you see the central location I mentioned before. There is some advanced logging features like decision logging to really understand how PA decided if it's allowed or not allowed. That can help a lot with debugging or having some statistics and so on. The testing part also, we'll talk about it, and it's really flexible. You can pull in some external data within the policy evaluation, so to do some advanced policy evaluation that can be important. Artem will tell you how we integrated it with OpenStack.
Yeah, I'll do it like that. REST API is the only way, so I'm trying to speed up a little bit. At the moment in the Oslo policy there is a support for HTTP check. Well, there is a HTTP check, but in reality it's broken. That is basically what we have figured out, that for some services the data serialization is broken, or actually it's just the serialization doesn't work at all. For some services the context is broken, cannot be serialized. So just a summary, there is something over there, but it's in reality not working. What we are doing, actually there was already a talk about similar topic, or actually about the same topic in 2018 in Berlin. We went basically one step further and actually rolled out everything in production. So anyway, we are just introducing yet another plugin into Oslo policy, which is directly invoking OPA. Now the architectural questions: where do we run OPA? How many OPAs do we run? All the normal stuff. Generally, the OPA itself. By the way, please raise your hands. Who knows the OPA, at least from the concept? Okay, quite a lot. Good. Then nothing new for you, but for others, something a bit more new. Technically, the OPA itself suggests to deploy it in a sidecar manner, that you deploy the OPA instance as close to your code as possible because of REST API call, so you want to keep the latency as low as possible. Sidecar in Kubernetes is very easy. Sidecar in not Kubernetes is not easy. What we are doing is basically just a systemd with the container, but running on the same local host for every service. So basically, everywhere where we have OpenStack service, we also have the dedicated OPA container as well. One OPA per OpenStack API service. This is also one of the points that ideally, from the Oslo policy point of view, it was designed that every service is prefixing their policies with service type. In reality, this is not the case, and we just wanted to prevent even the eventual collision. So we said, okay, we just separate this completely out. So if on a single node you have two different services, you would need to have actually two different containers because they use different policies under the hood. And the smaller is the policy file, the better it is for the performance and for memory consumption of the OPA. Even though it is low, very low, but still, this is the point. OPA listen on local host only for the low latency. The built-in basic security, in the sense, what we try to do to explain here is that technically there is a possibility to add authorization, to add TLS on top of that, but you understand that everything what you add on that side is impacting your performance. So at the moment we have not done anything here, but it can be easily done as well. We have also implemented a way, so what if that container is not reachable and you are an operator, you got a call on Friday evening and everything is broken. So we implemented also a flag that basically allows us to do certain operations like fail close or fail open, how to deal with that. Performance impact, we will talk about that a little bit later. Translating policy files. We also actually written the generator that takes the policies from the source code of the services and generates Rego files out of that. So technically for you, there is nothing to do. You have your templates, which you can then extend and add additional possibilities, which is basically just a one-time job, but it is still really very tedious to write those policies explicitly to convert those 3 lines expressions from Oslo policy for Keystone to translate it into Rego is a nightmare. But it's basically basis on the same context, like at the moment there is a generator that generates a policy YAML for you. In our case, it's not only generating policy YAML, it also generates a set of Rego files. This is one example of the policy YAML file, just as easy as it is for simplicity reasons, but is already describing one of our changes that we did in our cloud in the glance, how to make image, or the call to make image public. So by default, it is an admin only operation, and we wanted to actually have a different role for different set of stuff that would be able to also make image public without giving them admin, full admin permissions. So extended it with these funny or conditions with brackets, without brackets. Now how it looks like, basically technically you see the OPA prefix is basically exactly like the check that is involved. This is pointing to the plugin, which is then doing all of the madness inside. And this would be how the OPA is looking like. You see a couple of comments. Those are basically just to keep it, to make it more readable. So you see there are a couple of different blocks. Technically speaking, the OPA decides, or actually is capable of making fast decisions. So if it sees at least one of those is matching to true, it stops evaluation of all the further rules, and it goes in and immediately returns the result. I need to admit, Rego is relatively complex. It's not easy to understand, but it takes you roughly like 2 days fully into Rego topic, and you can read it and write it. And the next thing is that with Rego, you have possibility to write tests immediately for your policy files. So yeah, this is basically, you see the whole long string is also generated. So we are not only generating policies, we are also generating tests for the policies, which allows you then to do your next step and start extending them. And yeah, unfortunately it needed to be that long to prevent collisions and so on. But you see here, we can write as many tests as possible, simulating different inputs, different input for the policy evaluation from the data point of view, different contexts, like what are the user privileges right now, and so on. Okay, so how do we manage all of that? We have just a single Git repository where all the policies are placed, upstream versus our branch, in the sense of we take upstream OpenStack, convert them to Rego, and then we do our specific changes in the dedicated branch. From the CI/CD, then unit testing is running. Unit testing in the context exactly of Rego tests are being executed, and the OPA bundle is being created, which is then technically a CI container, which is then fetched directly by the service then locally. So we actually do not distribute the policies at all. So OPA on itself has a built-in refresh configurable, if I remember correctly. So every like 1-2 minutes it checks whether the new image is available with new policies, pulls it and activates that. Bundles are stored also locally for the context that all of a sudden you have no internet connectivity to your central registry, so it stores them locally and is able to restart. Neutron. Very special, and there is a quite a bold warning on the neutron side that neutron wouldn't be neutron if everything would be correct. So the policy evaluations in neutron are very different, and therefore it was really challenging to actually get this done. Neutron is doing few different things, and is introducing actually custom checks directly in the neutron code. Like one is owner check, which is when you are, for example, trying to create security group rule. It checks that the security group to which the rule is belonging also belongs to the same project. The same actually for the subnet creation, whether the network belongs to the same project and stuff like that. So it's basically checking the ownership of the parent resource. Field check is basically doing something very similar, but is allowing you to fetch certain attributes of the parent resource. And the policy evaluation is done completely differently. So in every other service except of Neutron, the policies are being evaluated before the request is being processed. In the Neutron, it is being actually depending on the use case. For listing, for example, first it goes to database and fetches all the resources, and then for every entry it evaluates the policy, basically filtering out entities that the user is not allowed to see. For create operation, it is again different. It's actually sending the full data into the policy evaluation, whether the user is allowed to create a resource with this data, which is also not the case for all the other services, which makes totally sense for Neutron. So great job. It's done in a completely different way. For updates is also different, but for the listing operation, this is something where the huge performance problem is actually happening. That imagine you have a project with 1,000 ports, means that 1,000 ports, you have 1,000 evaluations to filter out ports, and then you have additional 10,000 policy evaluations to actually check every single attribute of that to filter out the attributes that user is not able to see. So while the single Oslo policy evaluation takes just microseconds, when you are coming into this particular use case, it immediately goes into a question of like 10-20 seconds just for policy evaluation. So yeah, it was really hard job, but we actually ended up introducing Neutron DB proxy. You can have actually, if you have possibility, you can take any reasonable database proxy, just re-exposing the data of Neutron from the database. But we wrote a tiny application that only accesses certain pieces of data from the Neutron and re-exposes like really only the project like status, stuff like that. And it does this with the caching so that OPA invokes it only once, because all of the properties from the Neutron point of view cannot be actually changed. You can't change the type of the network without actually recreating the network. Therefore, here we can completely rely on caching and only read it once. Production rollout, what's the timing? How much time do we have?
So it's fine.
Okay.
Yeah, just a few words on production rollout. So our goal was to roll out this new OPA thing without impacting our users in a bad way. So both without like starting to deny things which should be allowed, and maybe the reverse could be even more problematic. And also on the performance perspective, making sure that we don't make the time to do API request, to increase the time for API requests. So we first introduced OPA without like introducing new policies. So just same policies using the generator and so on. So we could compare exactly the results should be the same in terms of what is allowed, what is not allowed, and so on. We did it per service, so started with maybe some smaller services that are less used in our cloud, and no Manila, that kind of thing, before getting to the more to the bigger ones. And later we then introduced our changes for our new roles that I mentioned at the beginning, our service member roles like compute member and so on. So we made use of Tempest tests, so the regular ones, and we wrote also some additional ones for our new specific roles. We also, without Tempest, also did some additional tests, especially like negative tests for these additional roles. Like basically, we wanted to be sure that okay, the compute member role cannot touch any of the other services. It's just the main point of these roles. And we have to keep an eye on the monitoring. I will explain a little bit just after what's the monitoring and logs. One thing is, so you see first performance, and remember, not a long decision is exactly, we kept an eye on if the number of notable decision was for some reason growing too much, because that would be a sign that maybe we are denying things which should not. So it is important to have all this monitoring in place. OPA itself, by default, natively exposes some metrics, some Prometheus metrics. some internal Go things, but at least also there are some things about HTTP requests. So here we are really talking about the request going to OPA, right? Not about the OpenStack API, but that gives us some information about how long it takes for OPA to process and answer to the request coming from Nova API and the other services. But that was not enough. So the good thing is there is this decision logging feature in OPA, which when enabled is able to give us some additional details about each decision, explaining how the decision was made, and it's pretty flexible how you then consume these things. And what we did is that we wrote this service called OPA Decision Exporter. So OPA is pushing all the decision logs to this OPA Decision Exporter, and then this OPA Decision Exporter has two missions. He has two things to do. First, it will actually write down the log somewhere, like in our logging system, so we can go and debug what's going wrong if needed. But it will also extract some interesting information, like how many requests, the size of the request, and the decision time. So for each decision, how long it took, and it will transform everything into Prometheus metrics. And from there, we have additional information, like the one that's important is like the decision time. Each decision, how long it takes, and I will talk about the performance just now. So the summary is, of course there is some additional overhead compared to Oslo.policy by default that is handled locally. Here we introduce OPA, so there is more round trip, HTTP round trip, even if on local host there is this overhead we cannot avoid. But basically each decision itself is taken in less than a millisecond. You see here most services it's less than a millisecond. This is here on the left the decision time, and on the right it's the HTTP request duration. So that includes the decision time plus the HTTP round trip. So on the right side it's a bit bigger than on the left side, but not too much. And what we see here is there are a few outliers, a few services which can take 1-2 milliseconds. So that's why we said the decision budget is 1-2 milliseconds. One of them is Neutron, and we can understand part of that with what
because sometimes we are doing round trip to actually check, fetch additional additional data from somewhere
proxy,
else.
I'm not going into the details for the rest. Things we can have a deeper look and see if that can be fixed. But it's anyway small numbers and not something that's causing any issues. So the performance impact exists, but it's this kind of impact. It's pretty low, and for us it's fine. In 1 minute I can just tell you about this timeout issue, which we spent quite some time trying to debug. We basically
a couple of months.
So we noticed in the logs of OPA some strange errors sometimes happening where, so not of OPA, sorry, of the OpenStack services, like on the logs of Nova API, Cinder API, Neutron API, Neutron server. It was complaining that it was timing out, waiting for an answer from OPA. And I mean, OPA is running locally on local host and could not find any problem on the machine, any load or anything. So there was quite a lot of low-level network debugging involved. We tried to reproduce it on test environments. It was hard. We somehow managed in very specific conditions, but it was very strange. And we look at various things. One thing we did is we increased the timeout. By default, the timeout, like the oslo.policy OPA plugin was waiting 1 second to get the answer. We increased it a little bit. That helped a bit, but the problem was actually still there. So we looked in the different Python layers, trying to go around some URL and other Python modules to see if there is something wrong there.
We got rid of request library as such, really, going directly to the, how was it called, under the hood. What's the request library is using under the hood? URL, thank you.
But it did not help. We tried to tune the configuration of the OpenStack service, like the number of rinse threads and so on. We tried to move our open services to UBSDI because it's something we had to do anyway, but in production, in the end, it was not enough. For now, what we have is it's slightly better than increasing the timeout. We have a retry mechanism. The thing is, this timeout happens really not often, like maybe a few times a day, and we have a lot of requests, right? So it was really a rare occurrence. Right now we have this retry mechanism, and whenever this happens, it retries once and it always works. So basically, for now it's fine, but we haven't really found the root cause. We think that basically the Python stack, the version of Nova that we are running is not the newest, and so the version of Python beneath is also the newest. So we will we are currently working on an upgrade, and we hope it will help. Yeah, I think it's the end anyway. Yeah, we have 1 minute left for the conclusion. You want to say words?
Yeah, a couple of words. So TLS is definitely something what we plan to add, but we just know how much additional cost it would be there for, well, something to be really very careful about. The idea that I'm actually also talking in one of my next talk on Keystone and G, which is actually taking approach of like neutron and reworks completely how the policies are being evaluated. But anyway, I was starting to think that potentially instead of keeping the policy somewhere centrally, we could integrate them into the Keystone, which originally had even support for that, but then it was deprecated. So technically it could be done this way, so that the OPA processes simply go and connect to Keystone and fetch the actual policy, so we bypass additional stuff. We also think about self-service roles, and this was actually exactly the direction into which we were thinking. So technically speaking, now we are able to provide possibility to the customers to create their own service, self-service roles. Yeah, this is my talk today. And additionally, what we are thinking, I forgot what we are thinking. We are thinking too many things really to do. Yeah.
If you want to know more, Artem wrote a quite interesting blog post with much more details than we were able to tell you in 30 minutes on his blog. Some references here. I want to thank also two other colleagues from CC11 who are here. At least Bodo, I see, is in the room. Maybe Benjamin is somewhere. We worked all together on these topics for the last months, so it was really teamwork. Thanks to them. And if you want to reach us, yeah, here are our email addresses. I think we're out of time for questions. You can find us outside the room if you want. And thank you very much for attention.
One small addition to this neutron timeout thing, or not neutron timeout thing, but the problem with the duration of the policy evaluation. With the OPA, we can fix it and can make the policy evaluation for the case when you have like thousands of ports. Really, it's a question of like few milliseconds. So that problem can be really finally solved.